space dimension, which will be 2D. Go ahead to electrochemistry, where we want to select corrosion secondary. So we go to corrosion deformed geometry, then we select secondary, corrosion secondary to our work. So we're going to add this physics to our work. This will be using a secondary current distribution. Move to our steady, where we choose a time dependent with initialization, which brings us to our interface. So quickly go to our geometry where we add a rectangle. We want to add a rectangle, and we want to draw our rectangle. 0, 1. Same here. We want to choose the position as minus 0.01. Then we go ahead to build our geometry. We go on to add another rectangle to our work, where we also make here 0.01. Our height should be this plus a little change. We want to add a little change to our work. So 1, 2, -4. So we just want to make a little change to the height, and also to the position as well. We want to make a little change to the position as well, which we go on to build selected, as you can see. So we have built our geometry. Go ahead to booleans, and we want to make a union out of this. So we select both. We uncheck this. So we want to join these two to make it one. Those selected, and they are joined together, as you can see in here. So we can see that we've joined our two rectangles together to form a single unit. We can load our parameters from our work. We load parameters from file. We'll be using galvanic corrosion. Using galvanic corrosion. I like to search for galvanic. So these are parameters. We found it. That's galvanic corrosion with deformation, as you can see. We load our parameters. So after forming our geometry, We go on to add an electrode surface for work. So we add an electrode surface where we select where this electrode surface will be. So we select 2 and 4 for our electrode surface. We check the species conservation. Check that. Let's open to check all these sections. Okay. Then we can now go to the electrode reaction. So temperature from the model inputs, the equilibrium potential, we put in this expression. That's also our kinetic expression. We want to use a cathodic Tafel equation where we change our I naught exchange current density to this. We change our anodic current density to this. We move forward. And we go on to add a second electrode surface. So the second electrode surface will be here. And go to the dissolving species where we add value here. We want to name this as Mg. Then this is rho Mg equal M Mg. So that's what we change in here. After we go to the electrode reaction, where we number of participating electrons, we make it 2. We set this to be 1. We set the equilibrium potential to be this. Kinetic expression is, it's made of the anodic Tafel, which will be I O underscore. And this is anodic, which will be E N as shown. Add a limiting current density, which we'll define as ILIM, anodic, as shown, as we've done in here. So that's for the electrode reaction. So we want to check what we did earlier. Want to cross check and see if actually named everything as supposed to be. our electrolytes itself. We go to electrolytes conductivity, where we make this user defined, and this has to be sigma as shown. Go to our multiphysics deformed geometry, check. Our deformed geometry. So things set in here. Geometry, deformation also sets. Move to the non-deforming boundary. For the initial, go to the second. We want to select only 5. So we want to select only 5 for this. So we want to select only 5 for the deforming electrode surface, and we want to, for the non-deforming boundary, will be the rest as shown here. So we go on to check isolation. Everything sets, then we can proceed to check our time that we want to set. We want to set our time from 0 to 12 times 3600, and we want to end at 3 times 24 3600 as shown. This could be very clear for us. So we can go ahead and compute our work. Which generates our results as shown in here. So we've been able to generate our results as shown in here. We want to add a 1D plot group. 1D plot group to our work. Which we want to add a line graph. In our 1D plot group. So we want to select the data set from our steady solution 1. want it from the remeshed. We want to select, as we've selected our solution, steady solution 1. So your solver. We check our meshed. Okay. So actually, we wanted to, in our time dependent, wanted to make the steady extension an automatic remeshing. So I've actually gone there to do automatic remeshing and want to compute it again so that we can get that result, because we need a remeshed solution. So I'm recomputing it so that we can get our remeshed solution, because it's very important for our work. I just went to time dependent, came here. Okay, now, so we have our remeshed results. It's very important to allow us to plot our results. So now we have our remeshed solutions. Now we go to results, we add a 1D plot group, and we add a line graph. Now we can add our steady remeshed solution. So that was exactly what's needed for our work. So our time selection, we want to select from the first work, and we want to select here. We want to select from 2, 4, and 5 to 4, 5, as shown in here. We want to change our expression in here to CD dot I log under ER1. That'll give us the local current density. If we should plot, this is what we have. We have in this plot. So I want us to close this space in here. Then our x-axis data wants us to change the parameter to an expression so that we can use an expression of x in here for our work. As you can see, to actually make it look this way. So we want to duplicate this work, and we want to start from last. Let's plot and see. Okay. So from last, we've had our plots. We want to plot our work. So let's go ahead to open a file for this galvanic corrosion with deformation, which will open and add. We want to view as we have seen over here. So we go to want to add physics. We want to add physics to our work, new physics to our work. So we go and we add new physics to our work in here. So our physics, we come to chemical species transport. We go to transport of diluted species. Add to our work. Where we define the variables. We want this to be 2, we want our concentration to be CmG. We want this to be COH. That's done in here. We want to add a moving interface. That's under mathematics. We add level sets. To our work. Go to the parameters. And we want to load from file. We want to load our parameters from file, which will be under deposit corrosion parameters. We've actually added these parameters to this. Our definitions, we want to add a step to our work. Smoothing, we want our size of transition to be this. So, we want to add variables which will actually load from file. We want under deposit corrosion variables. This is not defined, but later will be defined. Later be defined as we move on the course of our work. Definitions, we want to add non-couplings and general extrusion as shown in here. We want to select a boundary for that. So select boundary. Our source frame, we want it to be this way. We want to use source map. We go to advanced and we want to set the tolerance to the closest points as much as possible. In our general extrusion, go to our transport of diluted species. We want to uncheck this convection. We want to make it migration. Move to transport properties. And we want to define the diffusion coefficient as dm on s dot bf2 plus dm e on s dot infl. And we want to also define Okay, so this is 1. Okay, now it's defined. The diffusion coefficient as well, DOH S dot VF2 plus DOH E LS V F1. If we start before this, we want to change the electric potential as well. We want to define it as Q. The charge number, we want it to be 2 and -1. Initial values 2 as well. We want to make here COH4. Sorry, this is 0. As shown here. Go on to want to add reactions. We select our domain. We define a reaction should be R as delta this also is R is called OH. It's not delta. Go to our transport diluted. Want to add concentration to our work. We select boundaries and we define our species. Should be me H0 as defined in here. Go to transports. We want to add, move to surface reactions. We want to add electrode surface coupling. Choose 2 and 4 for our electrode surface coupling. The reactions coefficient, we want to change this to local current density. For this, it has to be local current density. Number of participating electrons, we want 4. And so the section 2, we want it to be 4. Go on to add surface reactions, and we want to add another electrode surface coupling. So this is the second surface coupling that we're adding. When we select domain 5, we go to the reactions. Same here, we choose the second region, the number we want to for this section. And we want to start from -1 in here. Because we go to the level sets. We want to look at the level sets model. Where we define the reinitialization parameter. It should be this max for as shown in here. We've defined our parameter for the reinitialization. This side, we also have to define the parameter for the controlling interface thickness, which should be LSHM. For we set the velocity field to this value. Set this to this value. This expression. Move to the initial values and we set it as the fluid 2. We want to add an inlet. The inlets we select 2, 4, and 5. And we go on to add, once we've added an inlet, we have to add an outlet. Very, very important. What's that audio? So we want to add an outlet. So after selecting our outlet, we need to select which area our outlet will be, because we've already chosen where our inlet will be. So we select our outlet, and the outlet will be the outer areas, will be from 3, 6, 7, and 1. That will be our outlet. Go to our secondary electrode. We want to define our electrolyte conductivity, add an expression to it. That will be LS dot BF2 F2 plus sigma F1. F2, F1 plus linear. Go to our mesh. We want to add edit physics induced. For the first size, we want to make this calibrate for fluid dynamics. That's what we want to do for the first one. We want a finer one. For the second one, we want also extremely fine. We want fluid dynamics, extremely fine. Wow, work. So we move to our free triangle. We want to add, I think we have to add a size to this. Add a size to our free triangle. And there should be for a boundary. We select 2 to 5 for our boundary. Pretty fine should be extremely fine. Let's build and see how it looks like. So, seeing how it looks like for now. We move to 31. We want to uncheck certain areas like the deformed geometry. We want to uncheck this. We want to uncheck this. So we want to uncheck these two. And we want to compute. Get rid of this. It should take some little time to compute. So wait patiently for it to compute. Wait a little while. Now to wait for it to compute. To take some time. To take some time. we wait a while for this to compute. Take some time. We wait a while for it to compute. Yes. We wait for some time. It's actually taking a while. It's taking a lot of time. Really sorry about that. But we can't continue unless we're done computing. So I'll plead with you that we actually wait. I'm sure yours is not also done yet. So we're almost 50% through with the computing, still computing. Patiently waits. So wait, I think we're almost done. Almost done computing. Finally, we're done. That's great. We have our results now. Took about 9 minutes. So we click on electrolyte, look at the streamline, and we want to see the positioning. We want to do a separating distance of about, let's make it about 0.035. We want to also make the range. Okay, the range is 100. We want to plot, let's see. And here we have our results. We go on to the surface to our work. We put an expression as 1 here. Then we select our coloring. We want it to be uniform. We want our coloring to be uniform. We want it to be gray as well. Go to the surface and we want to add a filter to our work. We want to name this filter as LS. One greater than equal to 0.5. That will be our filter. We want to plot our filter. So when we plot our filter, this is what we have. You can see our filter in it as shown. We want to add a 2D plot group. We want our data sets from our remeshed solution. We want our data set from our, we want to select our time from about, let's say the last time in here. This is what we want to select, and we want to go ahead and add a surface to our 2D. We want to put this expression in here, and we'll go ahead and plot. This is what we have. We go ahead and add contour to our work. Contour to, we want to change the expression in here to s.vf1. Unit should be 1. Labels should be, we have entry, or then we have labels, total levels. So let's make our entry mode levels, and want this to be 0.5 as shown. Let's change our color table to different color. Let's say uniform. Make it black in here. And plot. So that brings us to the end of this work, and I hope we're able to plot our work, able to follow till the end. Thank you. And please kindly subscribe if you haven't, and if you have any questions, please kindly drop them in the comment sections. And don't forget to like the video. Thanks. So we start by going to our model wizard, select new, and we select our space dimension, work with the 3D, which we select. Then we come here to select our physics. So we're actually going to use a secondary current distribution for our work. So we go ahead in here, when we choose under electrochemistry, we have primary and secondary current distribution. We have tertiary current distribution. So we go just under primary and secondary current distribution, we select the secondary current distribution. Then we go ahead to add this. Then we move to our steady, where we have to select our steady. And we'll be dealing with the time-dependent steady. So we go ahead to choose time-dependent with initialization, which we add. So this brings us to our interface, our Comsol interface, where we have added selected our physics and our steady. So we go ahead to add our parameters. We want to reload from file, programs file, Comsol, multiphysics, applications. Then I think we can search decorative plating parameters. So when we search for decorative, it will quickly search for our parameters. Then we load it, we open, we add to our file, as you can see in here. So we've been able to load our file quickly, as shown over here. So I think we can start to build our geometry. We go to geometry, right click, then move to insert sequence, which we go ahead to add. And for our sequence, we'll be using the decorative plating geometry for our sequence. So this is our sequence that we'll be using for our work. So choosing decorative plating geometry sequence, we open, load. Okay, so now we have been able to load our sequence. Then we go ahead to build all. So that builds our geometry as shown in here. Want to show transparency as well. So as you can see in here, we go to materials. Check for materials also. We'll add our materials later, not now. So you go to secondary current distribution and you want to change the current distribution type. We maintain it as secondary for now. We'll be making some changes as well at the electrolytes. Also, we want to change the electrolyte conductivity to user defined, where we want to set this to K PPA. Yeah, as shown. So we want to go back to secondary current distribution. We want to add an electrode surface where we'll add to our work. So after adding your electrode surface, you go ahead to choose the domain. So we want to select domain 4. This where we selected to be our electrode surface in here. So as you can see, there are many sections. And we have the film resistance. Now we move down to boundary condition. We have the perturbation amplitude. We have the external electric potential. We have different expressions that we can actually change them to for the boundary conditions. We have average current density, total current, and many others that we can actually change. So we are maintaining this to be the electric potential. Now for dissolving depositing species, we want to add. So we go ahead and select this area. This is where we're able to add our species. So click on to add, and it has added a species to it. So we have S1 being density as this and molar mass as this. So we've added our dissolving depositing species to the electrode surface in here of our work. So like I said earlier on, we selected domain 4 for our electrode surface in here, and we went ahead to add the species, but we want to modify the variable for our species. We want to define it based on our parameters. So we go ahead to define this as N I. We want it to be the RO, RHO, and I. We want this to be molar mass of Ni as shown. So we go ahead to open the subdivision for electrode surface. Then we go on to check the number of participating electrons, stoichiometric coefficient for dissolving depositing species as well. we've seen that what we change when we change the variable over there, it has been defined over here. We want to change the number of participating electrons to 2. We want to change this side to 1 as well. And this is the equation that Comsol will solve it with. Goes down. Then the equilibrium potential changes to this Q and the Ni. Then move on to the electrode kinetics, where we want to choose, before that, we want to choose the local current density. So we go to electrode kinetics, then we select our expression type to Butler-Palmer equation and change this current density to this underscore nickel I Ni, non-nickel Ni. So we've changed the current density this side. And move ahead to duplicate this electrode surface. We have a second. Move to the electrode reaction where we compare, but before that, it has to be changed. The domain has to be changed. It has to be changed to this. That's for the second surface, and also the phase has to also change to average as shown over here. And this expression too has to change to this. As shown in here. Then move back to here and also the coefficient has to change to 1, has to be 1. So we go ahead to the electrode surface and we want to add a reaction. We've added a reaction. We've added a reaction to this. Okay. So move ahead to the reaction. Then we want to move to the number of participating electrons. We will move to the potential. We also move to the kinetics. We change to cathodic. Current density has to change to this. Change this section to this. Then we go ahead to the mesh. As shown. So we want to change the element size to a final. We want to build all. Able to build. Go to our time dependent occurrent distribution initialization. We want to change this current to secondary. Then our time dependent, we want to change the output times. Let's change just this section to 60 and 600. Then we go ahead to, we can study now, compute. So we've been able to compute and we move to our results. So we move to the selection. We want to select just a particular area, which will be the boundary. We want to select this. We want to plot to see. So that gives us the thickness change. We want to rename this plot to the projected thickness cathode. We want to duplicate this. We want to rename as the current efficiency cathode. We renamed it. We want to look at the surface and also change the expression in here to CD ILOC underscore ER1 CD.ITOT. As shown. We've changed the expression in here. Then finally plot final work as shown. So that gives us our plots for our work. So at the beginning, we move to our new, go to our model wizard, then from our file, we look at our application library. So when we open our application library, it brings us to this space where we choose lithium-ion batteries and we select capacity fade. We select the capacity fade seed, we open. So when you open, it will take you to the interface and you see all everything defined, the variables. As you can see, variables have been defined over here. So it's actually inbuilt. All these things are inbuilt in the Comsol setup, depending on the model that we are using. Go to lithium-ion battery, electrode, everything. You can see it has already been, the domain has already been selected. Open our particle electrode has actually been defined. Most of the variables have been defined. Move to the porous electrode. So this is basically how it is, and if you should check the materials, you see that it's actually added materials to it. The electrolyte, negative and a positive electrode have been added to it. Go to the initial cell charge distribution. You can see everything has been input over here. So we go ahead to add a charge discharge cycling to it. That will be the first work, and we'll select our domain as form. That is all we select for this section. Discharge current, discharging current we set as -I. Minimum voltage we set as E. Maximum voltage will be max. And charging current will be set as this. Then we check this side, which is include constant voltage charging. And we set this side, which is the upper cutoff, as 9 charge. We would like to start, we go to the start mode, and we want to start with the charge first in this section. We move to porous electrode 1, where check to we want to add SEI as rho SEI. We want to make this here this way. As our dissolving depositing species. We set it as SEI. We define the density in the molar mass as well. We go ahead to check this add volume change to, we uncheck this part. And also the film resistance, we want to change it to thickness and conductivity, so that we can define the reference film thickness, which we define this way. And we also want to change the film thickness. We want to change it to total film thickness this way. Film conductivity, we want to change it to this. We move to the porous electrode reaction 1. We check everything. Then we go and we add a porous electrode reaction to the second one for porous electrode. So over here to go to the electrode kinetics. Then we make here user defined, so we can input our I. Let's go on SEI. Cycle. And let's go on number greater than 0. This way. Move to our variables. We check to see if everything is defined. As previously, those which were in yellow are now black. Everything is now black, as you can see. Go back to Pros Electrode Reaction 2. And we check our coefficient over here, which will make it T underscore factor -1. That is stoichiometric coefficient of V I theta. We go to our parameters and we check our T factor, that's time acceleration factor. Actually 250, yeah. So move back to our Pros Electrode 2 so that we can set our SEI to be T underscore factor. Our temperature should be user defined. We go on to definitions to add an integration. Where we select the negative electrode. We move to our steady. And before that, I want to show default. So we move to our current distribution initialization. want to check if everything is in line, but first you will actually modify this part and go ahead to disable our pros electrode reaction too. So you could either click here or just disable over here. So now it's disabled. Our pros electrode reaction too. So you go to current distribution, then you go on to disable pros electrode too. Let's open this solver. On our time dependent solver, let's add a stop condition. So we want to add a stop condition to this. That goes. And we also want to add changes part to steps before and after. So this section, we want to uncheck this part. Move to our steady. Want to uncheck generate default dot. So before you steady, you need to go to, you need to check all the areas to see whether there's no mistake, especially for the pros electrode reaction 1 and 2. So we check that it should be same that I've done over here. Material should be graphite, equilibrium material, kinetics as well. This way carefully set it. So this was what we made some changes over here. At the equilibrium potential should be user defined, kinetics user defined, so we go ahead and compute. we have our convergence plot. So we have this. So we move on to close this. I want to add one B plot group. I want to add a 1D plot group to plot some results, which we'll name as load cycle. Name this as load cycle with the title type will be 9. Plot to y-axis. Our load cycle, we want to add global. We want to input this expression and cell. So now variables I cell is already stated. Move to global. We want to duplicate this. We want to filter as well. We want to put a logical expression over here as first cycle filter. It's been stated in here. We move to global 2. And we want to delete this global 2. Just maintain this global 1 and duplicate it as well. I want to check this. I want to change this expression here to E. When we plot, this is how it should look like after plotting. We want to add 1D plot group. Change the expression to discharge. Is comparison. A title to none. y-axis, rename it as cell potential. Want to add a global. I will name this as the first cycle. We put this expression in cell. Direction. Want to change, check and make the parameter an expression. So we input our expression as T as this. This will be our expression for our parameter. And we go ahead to filter and we check this as first cycle filter charge filter. So this has to be, let's go. It's just a star over here. First cycle filter. It's a filter here. Yeah, and you're able to plot it. Move to your variables. See, first cycle plotted. Go ahead to duplicate this. How about we check the last cycle? and make this description cycle go to 200, 2000. And we go ahead to filter and make this the last. So we plot, we see. That's the cycle for. So we make here description cycle for 1. Make the comparison a bit better. We plot. This is the first cycle, and this is the cycle for 2000 to 2000. Go ahead to add a 1D plot group. Change this to SEI, layer potential drop at 1C. Change title. Y-axis. And we change the title to this. And go ahead to label the y-axis as potential drop over let's make this potential drop over CI layer. Go ahead to add a point graph. Select what we want to check. We put our expression in here. Change your parameter to an expression. Change the expression over here to cycle number. Change the description to cycle number. Change the things to at negative electrode current collector. We move ahead after adding move to add a filter to it. So we label this as PCH start and filter. We'll duplicate this. In this selection, change it to here. We delete this. And here is that of the separator. To show our legends as well. We duplicate this and change this to electrolyte. While this label changes to electrolyte interaction. And go to our points. We'll change this to yes. We change that of when you have to down one plot, we have this. Plot, we have this graph. I want to add another one, the plot group. Which we'll call capacity fade versus time. So capacity versus time. I'll try to be none. Y-axis show the time and days. Then show relative capacity. Go ahead to add global. This becomes Q minus 1. Q score differential Q of 0. Change the parameter to expression where I name this as T. Pattern. Let's choose T. Description. I'll just choose time as is. We show legends to now. And we want to show this as based on calculable 18. Go ahead to add a filter to this. Yes. Charge. Filter. Want to duplicate this and to C1 dot T underscore D which starts one change legends to nominal one charge capacity. So we will duplicate this. Change this to versus cycle number. Change this to cycle number. Expression change to cycle number. Send this to the scene. We plot add another one deployed group. Sorry, local state of charge at separator electrode interface. This manual. Y-axis is SOC. We add a 4-point global. We add a point graph instead. So select put the expression SOC OC underscore surface SOC, LOC. This is right. Make sure everything is right. Parameter expression. We choose to cdc.t underscore ch. But we want to show our legend. So need to show this photo. It's probably let me retype this again. Make your so legends show negative electrode to first cycle. Let's add a filter. It will be the first cycle underscore filter. We want to duplicate this point. And graph. We want to select this and select side 2, 3. This will be positive. We want to duplicate this again. And change the filter to, want to duplicate and change the filter to last. Sorry. Last. See. I want to duplicate this. Point graph 2 and select it's already selected, so select again here So we have 4. 1, 2, 3, 4. Already selected. Right? We move to. Want to check how variables will actually look. So in our battery, we go to how about look at cross electrode reaction. So this shows the local current density. Before that, for this I'll plot for our local state of charge at separator, electrode charge cycle. Try to attention. So basically that's it. Being able to plot our graphs, and this brings us. So we start by going to our model wizard. We choose, which brings us to select our space dimension. So this will be dealing with 1D. We select 1D. Then we add our physics. We have to select our physics. So normally to choose lithium-ion batteries, you have to select electrochemistry, come to battery interfaces and choose lithium-ion batteries. Then we add, then we move to our steady. So we move to our steady. Here we have to select the steady that we're going to do over here. So for our steady today, we'll be dealing with an AC impedance with initial values. So this brings us to our work interface. As you can see over here. So we'll be loading our parameters from a file. We'll also load our variables from a file as well. So I'll quickly take you guys through how to load the parameters and the variables from our file. So we click on parameters, as you can see over here. Then you select load from file, which brings you to the files where we have the parameters over here. So you select the one battery impedance parameters, as you can see over here, impedance parameters. So we've actually loaded our files over here. You can see all the variables that we're using from our parameters, their value, description, and all that. So we see the thickness, negative electrode, thickness, positive electrode, thickness, separator, and many other things over here. As you can see, all these parameters or variables will be used for our model today. We go on to definitions as well to add variables where we'll load some file and we'll choose our impedance. We'll choose our impedance variables over here. So that one is impedance. So as you can see over here, our battery impedance variables. And we load all these. So kindly note that Comsol has detected some of these expressions as unknown since we've not defined them in, we've not yet defined some of these variables, but as we go on, all these unknown variables will be known, will be defined, and they will turn from this color to black color. So I'd like us to quickly start building our geometry. We build it using a 1D, so we can add an interval. We build by adding intervals to it. So we first build our negative side. So this is the length of the negative electrode. And we build selected. And as you can see, we've built our negative electrode, the geometry itself. So move on to add another interval for the second. We specify the coordinates as intervals, as you can see over here. And we define the left end. And we choose the length, which becomes that of the separator. Then we build. So as you can see, done that for the separator. So we continue this way to build the rest of our models. We add another interval. Choose interval length. ET plus separator plus positive. Build selected. This should be underscore. So we go ahead to add our materials, where we first choose our electrolyte. So we add this electrolyte. Double click to add Afterwards, we add our two electrodes, our negative electrode, then we go on to add our positive electrode. That's done over here. We close this material library so we can see our model builder clearly. So we've been able to build our geometry, we've been able to add our materials, we've been able to add our parameters, we've been able to add our variables. So we go on to add a domain point probe. Where we define here as our reference electrode, which is RE probe. Go on to define here as so since we've chosen half of the separator, it was actually indicated over here. Open here, and we see our probe point probe expression. So we change the variable name and we define it this way. So we want to make this small caps. It's a bit better. So if we should go to our variables, we see that all our variables are now defined. You can go ahead now and quickly add, go to non-couplings, add integration. So we select a boundary to be at the end. For this. We choose, go to lithium-ion battery, right click, then we choose add a porous electrode. So we add our first porous electrode, but we select where it should be. We've selected that it should be at domain 1, which is the negative electrode. Go to electrode properties as well. And the electrode material should be negative, as we've indicated, clearly indicated. Move on down to check the film resistance, and we want it to be surface resistance. So we want to change the value of this film resistance to Flow resistance for the negative has been defined in the variable. And we want to change the electrode volume to this. We want to change this to this. Electrolyte volume fraction as well. We want to check the electrolyte conductivity and make a user-defined. We want to add a correction factor as well. And the diffusion, we want to make it user-defined and also make it same as well. Same as we did for the correction for electrolyte conductivity. Done same for the diffusion. We want to look at the particle interpolation as well. Look at the particle material, which should automatically be, we have to set it for the negative electrode. Initial species concentration is set to we set it this way. And we set the particle mean center surface distance as this. We check the porous electrode reaction as well. Check the material, make sure it is the negative. Change the reference exchange current density as well. We add the porous mixed double layer capacitance to our porous electrode. Where we change this double layer capacitance, we input that of the negative electrode. So it's for the double layer capacitance at the electrode, at the negative electrode side. We go on to add the second porous electrode, which will, since we've done that for the negative, you have to do that for the positive. As we need to change the electrode material as well. Has to be that for the positive. Do that for this film resistance, which has to be surface. Do that for positive. Change the electrode volume. Electrolyte volume as well. Change electrolyte conductivity should be user defined. And diffusion user defined should be same. Go to particle interpolation, choose our material, MCA. Select our initial species. Particle mean radius, mean center surface distance. I have to select that for the positive. Go to the pro, select the reaction as well. Our material start with the positive. We change our kinetics. We change this to this expression. The active specific surface area has to be user defined. So we add a porous matrix double layer capacitance. L positive. Double layer capacitance is also user defined. It's positive. Go on to add a separator. We select the domain for the separator. So our electrolyte volume fraction is epsilon separate has to be user defined conductivity has to be epsilon sep sep. Diffusion has to be user defined will be same. Yeah. Our initial values is checked. We will make some changes at the initial values where we change some of the values in this section. So we'll first change the electrolyte potential also change the electrolyte salt concentration. And we want to add another initial value which will override domain 3. So we add initial values, the second one, which will override domain 3. So we take the same value this has to be a negative at the end. This goes to initial. This goes to want to add electric ground to it, which will be at this first point. We want to add an electric potential as well. which will be at the end. This. If you want to define as this, we want to add harmonic perturbation to our electric potential. We'll define here as we want to add additional porous electrode material as well. It should be that for our positive, as we've selected here. The input here. You click on the porous electrode reaction. And you want to disable this part. And afterwards, we want to add a porous double layer capacitance to this effect. We want to change this to 1. We want to set this to a user defined. S OS 1. So just have to make sure all your expressions are named correctly. We go to our mesh where we use a user controlled mesh. For our work, go to the first size. We want to custom it. We want to set here as 1. Want to go to size 1. We want to select just 2 and 3 for this. Want the maximum element size to be 1. Secondly, set the far end, include the far end in a custom set this as 5. Set as 5, set for 27 to see how it will work. So we uncheck this and this. We go to our frequency domain perturbation. We go to our range. This way. Okay, so you notice there was an error. That means we typed place wrong at this should be at this end. Should be this. So we can go ahead and compute and we'll be fine. Good to go. So that's actually worked now. We've actually been able to compute our work. Now we move to steady. Then we want to open our solver. Look at this solver. Solution solver. I want to copy the solution. I want to copy the solution. And we want to paste. Now that we've copied, we have to. So we are going to paste it. So we first name this one not optimized. And we'll paste this, the one I've copied it, in a different section. We add a table. We want to name this as experimental impedance table, which we will actually import. It's a CSV file. You can see over here. We have experimental data over here, and we would like to name this as a reference electrode. Probe table. We move to probe.group1. We want to name this as reference electrode RE. We want to add a 1D plots group as well, which will label as the Nyquist plots. Label this as the Nyquist plots. We want to change our data sets to a different one. We want to use the not optimized solution. We want to change the title to none. Let's check y and x axis, which is very important. Want to use omega this. We want to paste this here, but we'll change this to imaginary. So that's brackets. So now Nyquist, we want to add a point graph, which we'll select for. You can also actually click here to paste. It's the same. Now expression will be imaginary C ground. It's giving us the units automatically. Parameter, we want an expression. We want the real C ground. We should dates. We have our plots here. Coloring. Line solid. Let's make it 2. Show our legends. Let's input manual, show, call this cell impedance. How about that? We will duplicate this as well. The label will be impedance for NCE versus reference. Okay. Over here, we change our expression. We make here E should be reference of NCE. The expression down here should be same. As we've done over here. We have real zero reference NCE, imaginary zero reference NCE. Take this to name our legend. And we have our plot. We go on to make a duplicate of the same work. And we add we want to make this LTO versus reference. So in here, change this to LTO. So for our expression for the Z, use LTO. As well, we use LTO. This as LTO. It's plotted here, as you can see. We move to our Nyquist plots, where we want to add a table graph. Table graph, we select it as experimental. Impedance. And this is reference. Our table, we want to select the experimental impedance table. Our x-axis. So this is our experiment impedance table, the one we imported. Our x-axis, column 2, third column should be manual. So this is actually column 2 is always real and column 3 is imaginary. Go to legends where we want to show our legends. I want to name this as experimental NCA. So it's plotted in our graph, as you can see. Experimental impedance NCA. Legend, we want it to be upper left this way. Want to preserve the aspect ratio. We want to plot as you can see. We want to conduct a parametric sweep. Go to steady one. The parametric sweep. And how about the load from a file? Load from a file. Load from the file here. And we choose the impedance parametric sweep. To see how the values will be. To study, to see, to compute and see. we go to parametric solutions 3. We want to make it parametric sweep. Want to put an Nyquist plot. We want to duplicate. We want to change the duplicated one to a Nyquist plot parametric sweep. We look at the impedance this side, and we want to change data sets from here to parametric sweep. We want to change the legends to as well to reference original settings. We want to input these. TDL plus so minus 2. Alpha positive 1. So, we have this minus 3. This should be this should be alpha minus 5. Change this to Yeah. And two. Omega n times 5 omega n this is this. Alpine plus 4 10 minus 7. Okay. 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 Right. What's the point graph? And we want to disable this point graph. Impedance, we want to disable the impedance for that, so we can see our plot. Now we go on to add physics so that we can add optimization. We add a general optimization to our work. Let me close this side. We want to add a global least square objective. So after adding our global least square objective, we want to browse and load our experimental file. So we've added our experimental data. If you have any experimental data, you could actually use it as well. You want to add a parameter column to this, which you want to define as frequency. So that's the parameter column 1, that's the frequency. We want to add a value column. So this value column will give us this expression. Let's go and see. To name this as the real impedance. To name this as into 6. Move to the value. We want to duplicate this. We want to make this imaginary. This also becomes imaginary. So we have the real and we have the imaginary. We want to add a steady. Which is within lithium-ion battery. We want to choose an AC impedance. So we move to steady 2. We uncheck these two. So under steady 2, we want to add an optimization. We want to use this type for our method, SNOPT for our method. This actually increase the tolerance, reduce the tolerance, and the least square frequency, let's make it from the least square frequency instead. So we've actually made this from the least square. Down, and we want to set our control variables and parameters. We want to set that for I naught positive exchange current density. Film thickness of the positive and we will then set the initial value for this. We'll make set as 1 exponent -3. This will be 1 exponent -3. We add that will be the CDL positive double layer capacitance for the positive. We add another that will be CDL underscore volume of positive capacitance, volumetric capacitance. Here we set as 0.5. Here we set as 5. 1 exponent 5. I like to expand this properly. So we want to set this upper bound 1 to 6. We want to set this to 1 exponent -6. So 5 exponent -3. 0.1 1 exponent 5. Which is set here to be 0.9. Which is set here to be 1 exponent 6. So after setting, we move down, then we go to output while solving. While solving, we plot the default to steady to. We want to show default solver. Optimization solver. Want to make this the gradient method as numeric. We set intervals to 5 exponent -4. -3. This section. Go to our definitions, and we want to add global variable probe. So name this as exchange and input this positive. Want to set the output table want it to be same as the and it should be on group one. Want tables, want to add a table, want to name this table as optimized parameters table. Exchange current density output table. Want optimized parameters. We want to duplicate this and name this as the double layer capacitance. We want to duplicate this as well. We want to name this as a film resistance. Let's see. The film want to duplicate this as well. This will be the volumetric double layer capacity plus electronic So next, we want to also duplicate our next plot. This duplicate should be next plot optimized data, so it should be none for now. Should be steady 2. So No, this should actually be for, it shouldn't be here, it should be for here. So here should actually maintain, here should actually maintain. So these changes, the data set should maintain. However, that for the next optimization is what we have to change. So go to the next optimization, then this is when we change this over here, as you can see. Go down, then marker should be set as square. It should be in data points as well. All these will have to go. So simulated impedance NCA versus reference. Okay. Experimental. We want our marker to be square. Go to steady optimization. Now output while solving, we want it to be at the next plot optimization. That's where we want our output should be. So we go ahead and compute. Wait while it computes. So simulated blue and okay. Okay. So as you can see, our simulated impedance is our experiment. That's our experimental impedance, and we've actually optimized our simulated impedance to actually meet our experimental values. So if you should go to okay. Okay. move to about 10, and let's change this to optimized. We've seen our results being plotted. So this is how we do optimization for our Nyquist plots, and this is a Nyquist plot, an optimized Nyquist plot. So thank you for following to this point, and I hope you're able to make this result. Thank you. This dimension. Then, since we'll be dealing with 1D, we select 1D. Then we choose our model physics. We add our physics from, so we select electrochemistry. It gives us our battery interfaces, and we add lithium-ion battery. So once it has been added to our physics, move to our steady, and we select the steady that we'll be dealing with. So we choose a time-dependent initialization. Once we choose time-dependent initialization, then we click on done. So we move ahead to add our parameters, and we load it from our file. Comsol. We choose a 1D parameters, and we add to we load to our parameters, as you can see over here. So we're able to see all the parameters that we'll be working with over here. See all our parameters. So after adding our parameters, we move to the geometry, and we start to build our model. We specify, add an interval where we specify interval lengths to add an interval length, then into input from our parameters, the variables from our parameters. This is LNEG, this is separator, that below is a positive. We build selected. So as you can see, based on these variables from our parameters, we've been able to form our geometry over here. So from here, we move to global definitions, add functions, which will be interpolation, and the data source will load from a file, which will actually browse and load it. So select this, it becomes interpolation, and we import. So we import, we have PS over here, as you can see. So here we decide to change the name to EEQ. This, and decide to make here cubic spine. Here is function. We plot to see how it looks like. So after plotting it, this is how it should appear. So when you plot and it looks different, that means you've actually loaded a different file. We'll go ahead to name the function. The units. So the unit appears over here, as you can see. Move on to add another function known as the piecewise. So with the piecewise to reload, which is the load cycle, so after loading the piecewise, you decide to plot and see how it looks. When we plot, this is how it should look like. See the start, end, and function. So we change here to constant. Here we change to continuous second derivative. Make it 10. Absolute size. And you see how it goes. Move to make the argument s function is 1. Go ahead to plot, and this is how it should look. We change the argument at the top to be t, which we plot, so it becomes this way. We move on to add variables, which we will define as variables for the positive, current, vector, which will select a boundary at the end. We decide to name it I up PW 1 2 times I underscore 1 C over here, which we will describe as the applied battery cell current density. Move ahead to add materials from our library. Where we select the materials that you will be using. So we choose batteries, choose electrodes, and we choose dealing with this. So we select this for our battery. That's one electrode that we'll be using. We highlight the domain which should represent. So this represents this. When we open, equilibrium interpolation, and we plot. This is how it should look like. This is how the plot should look like. So we go on to add electrolytes. And also we have to select the domain. So we select all. Look at the interpolation and plot, and this is how it looks like for the electrolytes. So after adding our electrode and our electrolytes, we close this material section, and we go on to check our equations. So we see different types of equations over here, which represents factors in the battery. So we want to show more. And show more options. Equation view, advanced, click on OK. Come to our dependent variables. See our discretization, our charge balance bundle. Then we add first electrode. Which we have to select the domain for that. So we just select here and we select our porous electrode. Go and we select, we check all necessary areas we have to define. You actually look at the electrode material. And look at the electrical conductivity, which you will have to select user defined. We'll name it as KSN. So we've named our electrical conductivity as KS underscore NEG, neg, because we chose this negative electrode side, and that's where the porous electrode is. Move to the particle. Move to the porous matrix. Rename all integer. From here, the volume fraction, electrode volume fraction, and the electrolyte volume fraction. So name them as EPSS neg and EPSL neg. Move to effective transport parameter correction. Choose the electrolyte conductivity as user defined. And input this. Also come to the electrolyte conductivity where we choose no correction. Move to diffusion, choose user defined. We input the same. So electrolyte conductivity is user defined. Input this. Electrical conductivity, no correction. Diffusion is user defined, and correction factor. Input this. We move to porous electrode again. We expand. We look at other areas like the particle interpolation. Over here, we check the species settings, the particle transport. Change here to CS underscore neg. Change maximum species to user defined. Yeah, so it's a small caps C. We move to particle transport, where the interpolation, choose user defined DS particle mean center. Select this. the particle mean center surface distance. Check the operational SOCs for initial charge distribution. We select user defined. Also maximum electrode state of charge, select user defined. So we move to the porous electrode reaction as well. Check equilibrium potential. User defined. Which will define over here as EE. Unique. CS underscore surface CS max underscore unique. Okay, so like this is how it's supposed to be. Reference exchange current density to as well exchange to this. Temperature user defined for the temperature derivative of equilibrium potential. Remove and add another porous electrode. So we select the domain 3. We go down. Further, we check materials. Okay, overridden. Okay, so this has been selected as 3, and this is still not selected yet. By the time we are done, electrolyte is for all the 3. This has been enabled. We move to porous electrode 2, and we define. So we move to the electrode properties as we did for porous electrode 1. Change the electrical conductivity to be user-defined. Also, we select the electrode material we move to electrode volume fraction, which we define as EPS positive, SL positive, from there we move to the effective transport parameter correction to be user defined, correction factor positive, we move to the electrolyte conductivity set as user defined, then EPS also diffusion too as well, user defined. Is how actually EPS oh the correction factor as well. We move to the particle interpolation. Where we first change to this, the particle material. This as well changes to this. So positive. So that's for the initial species concentration. And we have the maximum species concentration be from the material. Move down to interpolation diffusivity. It should be user defined as this. Particle mean defined as this. Then move to particle discretization, where the element order will be an order of 2. At particle discretization. Move to the porous electrode reaction view. select the material, select the reference exchange current density, define it, we go on to add an electric ground, go on to add current density, so we move to initial values and we change the electrolyte salt concentration. Move to default inputs and we change this to T. Go to our time dependence and change to 8,000. Move to our steady, define where it will be. So this side becomes our electric ground. And since we've added our current density, define where our current density will be, which is minus A applied. So with everything well checked, everything properly labeled, check our interpolation, no mistake anywhere. You can go ahead and compute. And this is the plot that we get after computing. So you're able to plot the electric potential against the potential V. And this shows the average state of charge from 0 to 8,000. So we see the electric potential against it for a period of time. That's the graph of the electric potential. So we label the title properly. So that this comes here. Change this to cell voltage. as you can see here. Move down. The position should be at the lower right. As you can see, boundary. We check our point graph. So we move on to duplicate this point graph one. See, and we click this plot on secondary y-axis. As you can see over here, we will make some changes in this point graph too. I'm going to change the expression to I f clicking here will show you where the expression we're going to highlight. Go to definitions, go to variables. That's it over here, as you can see. If you double click on that, it will actually give you IF. So let's go on to plot it in it, and as you can see, it's been plotted together with the previous graph. So we go down to show legends, add manual legends to it. Then we name this as current you can see it has been updated on our graph. Select, make a selection as well. Go to point graph one. Just already be defined. We need to also show legends. So we go on and add a plot group. 1D plots. Go on and add a 1D plots, as you can see over here. Select the solution as none. So after adding a one plot group, we actually duplicate this. This is the data sets where we choose. No, we actually add a line graph. So we delete this instead. So we add a line graph to this where we select steady solution 1. We choose from lists, we select the 10 value, and we select all domains over here. We come here to change the expression to 0 plus 0.148. Show the legends, choose manual, which is 0 plus 0.148. Yes. So we duplicate this. And we change the expression to eta underscore 1. This can be found lithium-ion batteries, electrode kinetics. So as you can see, we can find this over here. So we change the radians to eta. As you can see. So we go ahead to add duplicates of line 1, which will eventually become line 3. So from our list, we select value of 1990 from our list. Then we input here as 0.558. This goes out. This comes 0.558. Eventually, the plots updates as well. So we move to next, which is 1D plot 6. We add, go to plot settings, y-axis, x. The y-axis becomes of voltage V. So when we plot it, it automatically updates as well as this. We move to this, we see it's this graph. You also select from list. You choose 1200 from this list. Then move along to choose, select again 1008. Move along to select 2200. Along to select 3000. Move down, then we select the show legend, selection is showed button, then we plot. So when we plot, we have this electrolyte salt concentration graphs to show the legend for all the times. Shows us all the time as coordinates and the electrolyte salt concentration. Move to plot settings, where select here as X and here as light concentration CL. A plot update. We add the 1D plots. Where we select a time selection from the list. We select 10. We select 1200. We select 1800. Sorry, 10. Move to 1200. Move to 1800. Move ahead to the title where it will be manual. Select this as manual. Select this. Okay. Custom now. Custom. Make it black. Default. Select the title as electrode particle lithium concentration surface solid and center dashed just like this, and this. Okay, so the plot settings too as well. X axis will be X, Y axis will be CS, mole, and mole, sub 3, sub that way. We add a line graph to plot group 7. To be manual, we choose all domains. We select the entire domains over here for us. We choose the expression over here, which will go to lithium ion battery, go to particle interpolation. We go to particle insertion. We move to particle insertion concentration. This one just after the solid phase concentration. So we select this, it appears, or we can actually just input this expression over there. It will show. So we move to show legends. Over here. Then we go ahead to duplicate this. As you can see, from 10 to 1,800 seconds. We go ahead to insert another expression. So go to lithium ion batteries, go to particle interpolations, and this one is the particle insertion. Go to insertion particle concentration. That is what we select for this. So you can actually go ahead and select, type this at the expression. It will actually give you the same. Comsol will detect that same expression. How about we change the coloring and style? Right, we make it dashed to see how it looks. As you can see, the dashed. How about we change the color and make it a bit this way. So you can actually decide to change the coloring and style depending on which will make your work look quite appealing or make you better explain your results well, or differentiate each result from the other. You can go on, change different colors. You can even make it dotted, make it dash dot, and make it circle, solid. So we want to go to our parameters and add just one variable, which we'll call C. The value will be 1, and we name it as the C rate factor for the parametric study. And we go to our definitions as well. Maybe we have to define it in our definitions as well. This what it actually means, or what Comsol should actually do with it. And we'll name it as the discharge current for the parametric we've actually added some one variable to our variables and a variable to our parameters to help explain to help us continue the next work we are about to do. Because if we do not define these parameters, we will not be able to do this. So we'll move to our definitions, and I want us to add another function that will be non-coupling, which will be integration. Select a boundary, which will be at the end of this. So we choose boundary 4, and we want to change the operator name to positive CC. As we can see over here, change it to positive CC. And we'll move to the electrode current density, and we want to duplicate it. So we have a second one over here. And I want to change the name to, or just include steady. Yeah, steady. So it's, and I want to change the inward electrode current density as well. Like this. Once we make this steady one, we want to move to the solver equations, configurations. Before that, let's add a steady, a new steady to this work. And I want us to look at a time dependent with initialization. Okay, so we double click on it to add it, and we close the side. So we've added another steady, and we chose a time dependent with initialization. So we move to our time dependent, and we change our range 0, 4, to the seconds. So we choose our times from 0 to, we choose 40000 for 40,000 seconds. So I would like us to modify, click on modify model configurations for our steady setup. And we will over here, we'll disable one of the electrode current density, which is 31. So it's either you click here to disable, or you can actually right click to disable. When you disable, it should appear like this, as you can see. Go to time dependent, and we will modify as well. We go to the current density, where we will disable 32. So for the second steady, what we did was we disabled steady 1, and for the first steady we disabled steady 2. So I want us to add a parametric sweep where we will vary this is what we vary. So I want us to choose these values 1, 2, 4 for parametric sweep. These are the parameter value list that we'll actually use. Move to our 32, time dependent, times 0. So we want to show our default solver for the parametric for the steady 2. We're going to add our default solver for steady 2. So for the time dependent solver 1, we want to add a stop condition. This, as when you go to solve solution 3, click on it, it will open several options, and you click on the time dependent solver. You want to add a stop condition to our steady 2. I hope you're all following me. So we click on add over here. We click on this button, stick it to the add. Then we're going to input our expression, stop expression. Now we want Comsol to check for us that when he sees this, it should actually stop for us. Comp1 is our stop expression. So we also want the output to be steps before and after stop. That's what we want Comsol to show for us. And we want to unclick this add one and check over here, uncheck it. I hope you're all following me on this up to this point. We'll go to study 2, parametric time dependence. Look at our times. So we've actually checked it from 0 to 4,000, 40,000. Click here, third group, time stored in output as well. And before that, let's go to a time dependent solver and check as well. Look at our output times. And we want it to be steps taken by the solver. So I hope you're following me to this stage, up to this point. Okay, so you move to study 2 again. I want to uncheck this generate default plots. Afterwards, we want to compute and see our results. So as you can see, our computation starts running, simulation starts running. You see our results. So if you followed me to this stage, you should get this result. So we want to go to results and add a 1D plot group. Want to plot some of the results based on the information, the computation that we just did, which is we'll use the data set from study 2 solution 3. That's study 2 solver 3. And we have study 2 solver 5 too as well. Parametric solution study 2 solver 5 as well. So this solver 5 is from the study 2. Stop condition that we added and everything. So we go ahead to add the parametric study 2 parametric solutions 1 solver 5. That is what we'll add. We want to add a point graph to this. And we want to select till the end of this as we choose domain 4 for this. And also we change this to this. So automatically change to electric potential. If we plot, you should have this result after plotting. Go to the parameter. Choose expression. And we choose so okay, so oh, sorry. I think I shouldn't have added this to this. The plots like this. We want to show legends. Do manual, we show legends. How about we change this to 0.1? See, we see this goes to 2C. Sorry, 2C, and this goes to 4C. As you can see. Go to the title. We actually choose manual, discharge curves. We plot. So this our electric potential against discharge curves, but we are not done yet. We change this. Meter. It's actually capacity. So this is our voltage. Yes. So we want to did the manual axis, which is here 20. We want to see how it look like. Okay. How about we make here 2, we make here 4.4. We thought so that's how it should look like. How about so we actually plotted our discharge curves, our voltage against capacity. Being able to, using a 1D, being able to draw a discharge curve. And you can actually see we should go here, piecewise. You see how piecewise? If we go to parametric sweep, seeing all our plots, so you can see. So before, and I think there's one part here I have to. This is voltage. Voltage. Yeah, so that was the last part. And thank you all for following up to this part, and I hope you will be able to make these plots and get these results. Thank you. By going to our model wizard, where we choose our space, we'll be working with the 1D space. So we choose 1D, then we select our physics. So we want to use lithium-ion batteries. So we click on electrochemistry, and we look for battery interfaces where we select lithium-ion batteries. Then we move to our study. We'll be dealing with time dependent with initialization. So we add to click our study. Done. It brings us to our interface, as you can see. So we look at our parameters and we want to load our parameters. Go. Programs files, Comsol files. Batteries. So we will be looking at choosing our parameters from here. So when you go to your programs files, applications, battery fuel cells, lithium ion battery, to bring it to this section where you have to load your parameters over here. And you can see we have several parameters that you can work with. There are several parameters over here that has been inbuilt in the Comsol setup, as you can see over here. So we will be looking at the battery, the parameters that we're working with is right over here. We're looking at battery multiple materials parameters, as you can see over here, and we load it. So it brings us here. And when you load it, you get all these parameters over here. So this is what we'll be working with right here. Our work today. We can go ahead to build our geometry. We add an interval, specify the interval, we'll make it interval length, and we input what the length will be. We want to use LNeg, LSEP. We want to add L positive. Afterwards, we build the selected, and it's been built over here. So afterwards, we can go ahead and add our material. We add from library. We choose our electrolytes first. Then afterwards, we add our electrode that we'll be dealing with. After adding your negative, you have to add your positive electrode too. So add our MO electrode too as well. And we close this material section. So as you can see, you have two positives and one negative. We'll look at the NCA, look at the basic equilibrium, and we look at the interpolation. Let's see how it looks. As you can see, and we will also look for that of LMO, look at the basics, look at the interpolation, and we plot to see the difference. See, there's a huge difference between that. Go on to add our variables, which will load from our file. We'll load from our file right here, multiple materials variables. As shown here. So these are the variables that we will be working with in our work for today. So it's very easy to locate where your variables will be if you follow what I'm doing exactly. We go to lithium and want to add a porous electrode to our work, and we select the domain, which is the first domain. We go on to choose. We look at the, before that, let's open our material section, then to close the side. So at the porous electrode, we go down and we define the electrode material. So we look at the electrode material here, and we want it to be, we've chosen here, so we want it to be the negative electrode, because this domain already is indicated as a negative. And we look at the porous matrix. We want to define this. And you see it's Comsol has detected it as an unknown variable, as you can see over here. But later on, as we move on, it will be defined. Go to the particle interpolation. Very important, we select the material, which is a negative. We go to particle transport properties, where we look at the species concentration transport. We want to change this to the selection in here. Then we look at the particle mean center surface. We should use that of the negative. Look at particle discretization. We want to change the number of elements. We want to make it 20. In this section. You look at the distribution and we want to make it linear, the particle discretization. And we quickly move to the Pros-electrode reaction. We look at the material, we choose negative. We look at the reference exchange current density. Choose this. Specify this. Go to lithium. I want to add another porous electrode. We select the domain. We select the electrode material, which is the positive NCA. We change this electrode volume fraction plus NCA. Change this to X. We go to effective transport parameter. Make this user defined. Correction factor should be this. Positive. And that of diffusion 2 has to be user defined. And the same as this. So we did copy and paste over here. So we move to the particle interpolation. We choose our material. Select our material to be NCA. Move to our particle mean center surface, which we change to RP positive of CA. We change the species fixed or to Baker. We did change it to Baker, so we change So we change this to this. And we go to porous electrode, we change the material to NCA, change the exchange current density. Oh. All should be in small cups. Then NCA in big cups. In small cups. Right. Okay. We go on to add an additional porous electrode material. We select the domain. Then the volume fraction too has to be changed. Like this. Add the particle interpolation. And particle transport species as this. Concentration. We want to change this to solid phase concentration. Defined in here. We go to the porous electrode reaction one, then we want to define the material. We define the material. You have to select the material for this. So our material is positive. Also, we have to change this exchange current density to this. And we change the concentration to insertion concentration. Okay, so some input just the small caps has to be small caps. I. So we go on to add a separator. which will select the domain. Separator is this section. And we replace the volume fraction set. Then electrolyte conductivity is user defined. As you can see, also copy this, same for the diffusion, has to be user defined. So we place this in here. So we go on to add initial charge distribution, the initial cell charge distribution. We want to make this section, the initial charge, battery cell setting as state of charge. We input this values as SOC underscore cell. Yeah. And this section is also underscore there. Now this is but we move to the negative electrode selection, and obviously we have to select this section for it, that because that's a negative domain, and also do that for the positive, select the section. So after doing this, we go on to check where our value was in, it's still unknown. It's because of, this should be underscore and it should be correctly named. So now that all our variables are, you go on to add an electric ground. Want to add an electric ground. We select a section. So it's this point that becomes our electric ground. Then we go on to add an electrode current, and an electrode current to this as well, which we select where to be at the fourth. go to defaults, and we want to click here and make our temperature T. We set it to T. We go on to mesh. We want, let's make it fine. Let's build. Okay. Let's go on to add an integration. Then we select boundary for this integration. We want it to be so it's fourth. Let's name this integration as, we set the operator name to be a different name over here. How about we name it as end terminal? So we set that section. How about we move to the current, and we go to the time dependent and we change to 0 to 3, 6. We go ahead to show our default solver. And our time dependent solver, how about we change the times to store as this. And we go on to add a stop condition. We add our stop, our expression. So this will be our stop expression. So our output at stop, we want to deselect and check this. And we want to uncheck the default plots. and we go ahead to compute. Okay. So we've been able to compute this. It has given us some results. We want to add a 1D plot group. Where we want to name this plot group as constant. Discharge. We want to add a point graph to this. Choose to end. We make a selection. If actually can actually paste this and it will actually be the same. I can use this paste selection to paste it. Right, you can just click on it and go to go. We select the expression over here. Go to lithium-ion batteries. This is our expression that we should be using. Electric potential. When we plot it, gives us electric potential versus time graph of it. You can look at the plot settings. Check and change what should be at the y and x axis. On the y axis should be the voltage. The title we want it to be this. We want to make some edit the axis. As you can see, so you go on to add another plot group. We add a 1D plot group. We want to name this as a surface concentration positive. and we'll add a point graph. We will select this and going to choose particle interpolation. Then is the after solid phase we have insertion, and insertion particle concentration surface. Legends want to name this as NCN. We want to plot this. So we have our plots here. We want to duplicate this point graph. Want to change the expression over here. We want to select the insertion particle concentration. So we have our insertion particle concentration. This is what we'll actually select for our work. So we just double click on it. It gives us this. Or you can just type this expression over here and that will give you the same results. So we have our plots being done. We go on to the surface. Title, we want to name the title as want to name the y-axis as surface concentration. To do some editing of the y and x axis. Okay, so we plot this. We've seen some changes. We want to change the position of the legend over here to upper left. Let's see. So we go on to a steady solution. We want to duplicate our steady solution one. We want to name this as, but we change this here to take the component from this first section. Material tool has been changed. Go to our results. We want to add a 1D plot group. We want to make this a particle concentration. Negative. We change the data sets to this. We do our time selection as interpolated. We need to add a range. To start from 0, step 200, stop at 2000. We want to add this to this. We want to add another range to as well. We want to start at 2032. Step will be 2030. Then 2200. Let's add it. No, we make this 2030 instead. We add another range. And this would be so if inserted or added our time range. We want to add a line graph to this. So we select one. Can also click here to select all, and we have to put our expression for this, which will be Okay. So we want to plot this, and here we have our plot. Let's check the x-axis. Name this as normalized particle dimension. We check this as well. We want this to be the particle concentration. And we want the title to be this. We add another steady. We go ahead to add a steady for this. Then we choose a time dependent with initialization. Steady 2, we want to change here to 600. We want to add the parametric sweep to this. We'll add the parameter for which we want to check it. So we choose this and we try to vary within these parameters. Go on to steady. We want to show the default solver. We go to solver 3. We want to see the time dependent solver where we want to make the output times steps taken by solver. How about after that we add a stop condition. We input the expression. Which will just be the same as, sorry, this expression. This expression. So you can copy and paste, but I'll type it again. Stop. 1 dots and that's the expression. Stop expression. We want to uncheck this, add warning sign. Okay. We want to also uncheck our default plots and begin to compute to get our results. We begin seeing some results. So we have our results. Now we go on to add a 1D plot group. We name this as voltage profiles. Voltage profiles. We'll make it parametric. We add a point graph to this. We take the data set from our parametric solutions. Highlight, select this point. Now expression will change to the electric potential. Our legends, we want to show manual. $95 volume 5-1 mix of NCA and LMO. $25/7 mix. That's 55/45 mix. And we have 75/25 mix of NCA and LMO. We have 525/75. Then we go ahead to plot. As you can see, we have our plot of electric potential time showing different volume mix of our electrode materials. We go here, we want to change the y-axis to, change our y-axis here. I want to name this as just the voltage voltage, and you want to, title should be manual, because voltage profiles for different mix fractions for NCA and NCA and O. So after that, we want to manually edit the x-axis and y-axis. Bring this to 0. Bring this to 3, and bring here to 0.2. We plot. Okay, so now it makes it more better. Then we want to change our legend position to the lower left. You can see over here. So we've been able to see how mixing different positive electrode materials will have on the voltage on the battery during a period of time, and we've been able to plot these voltage profiles for different mixed fractions of NCA and LMO. Also made a surface concentration plots for the NCA and LMO electrode materials. Also, we're able to do some parametric study on how these different mixed fractions will have on the voltage over a period of time in the battery. So I'm glad we're able to produce these plots in this work that we did today. Okay, so thank you for your attention. So we select 0D. Then we go on to select lambda battery. So we open electrochemistry, battery interfaces, lambda battery. Then we move on to select our study. We select time-dependent study. So it brings us to our interface here. So you can see. So we go ahead to add our parameters. We'll load our parameters from our file. So we go on to click here to load, which brings us here. Then we select our parameters. So we select this for our parameter. We go on to double click. Then it adds our parameter, loads our parameters. So we go on to add our variables as well. Which will load from a file. We select this and load. Now we have our parameters. So later we'll define all these variables so that they will turn from this color to black. We want to add table to our results in here. We want to name it as load cycle table. We want to import from here. So it's just after the capacity loss, we use parameter estimation just after this. So this is what we choose. And click on open to load our file. We go on to definitions, then we want to add, before that, we want to add function interpolation to this, which we will name as E and I versus T. Then our data source will be from result table. It will be load cycle. Our function name, we want to change this. And this as well. I want to change the arguments to S and the function argument S. Go to our variables and we realize that all these unknowns have been defined, now turn to black, which is very, very important, because if they are not identified or they are not defined, we'll not be able to compute our work. So we come to, we check this section as well. We check the applied current, which we'll be using. We want to define it. It's this. We want to also define the battery cell capacity. And also we want to define the initial state of charge. Okay. We go on to check the cell equilibrium potential. We want to clear this table in here. We want to load from file. We want to choose load our data from file in here. So this will be our file that we want to load. We want to change this temperature to T. We move to the voltage losses. Where we check all these sections. We want to include concentration over potential. We move to steady, then we want to make this a steady load. Load curve simulation. We move to our time dependent, then we want to change our range values. In here. We want to use user controlled and set our relative tolerance to very smaller decimal. We go ahead to compute our work. Which gives us our results. We want to set this as our cell voltage. Title 9. We want to also change the position to our right for our legend. We move to our global one. And we want to set this as our modeled cell voltage. Move to our global 3. We want to put an expression, go to our definitions, our variables, and we choose this. We want to make some small edits on the manual axis. Change this to 305. But we change here to 3.35. Y maximum change to 4.2 in here. We update. Here, what's our source stage of charge? Then we add a 1D plot group. That'll work. Then we'll name this as voltage losses and load, which will go ahead to add a global plot, add an expression, now come to our over potentials, where we select this ohmic over potential, double click to add. So we go on to add another expression. We add one more expression, which will be the activation over potential. We add also the concentration over potential. To this. Once we've added these three expressions, we go on to set the parameter to an expression, named as T. We go on to update our plots. We see our various over potentials shown in here. You can see our ohmic over potential, activation and concentration over potential over a period of time. We want to go on and add the global plot. We'll set this expression as the cell current. We choose this. Then we go on to set the parameter It's time. We want the line to be dotted. We want the color to be black. We want to plot this. So as you can see, it has been updated on our plot in here. You see the cell current in the graph. Go to our voltage. Take the title off. Want to know what the y and x axis. Want the y axis to be our over potential. You set our y axis to be over potential. And we want to add our global 2 to it. As you can see, it's been updated on our plots. You see our over potential work over a period of time. We want to edit our axis. So it has been updated after making some editing on our x and y axis, and how our plot has been beautifully plotted over here. So we go on to our component 1 to add physics, which we want to do a general optimization. We want to add optimization to this. So we've added our optimization, and we want to do some other, include some other optimization to our work. We want to optimize our work. We go on to add our global least squares objective, which we'll be using for optimization. Our data source, we want it to be from the results table. We want our results should be load cycle table. Our time column should be TS. And our model expression for this should be cell. We want to uncheck this. We go to our voltage losses. We want to set our diffusion, our temperature to T. We want to set our ohmic over potential eta. We want to set our exchange current density. We want to set our diffusion as well. Go on to add another steady, which will be a time-dependent steady. That will be our parameter estimation. We want to uncheck our default plot. We want to add optimization. Set using this optimization. I want it from least square objectives. Come to control variables and parameters, where we want to add about 3 ohmic inverse diffusion. So we set our scale 0, 1. So we set them as such. We go on to our definitions to add a global variable proof to our work. Our expression will be eta which will go on to duplicate this. It will be this. So we go on to duplicate it again for the third time. Change this to go to our parameter estimation and want to compute to find an error. So there was an error because Comsol detected that this variable is undefined. So we actually go to where this variable is located over here. Then we make sure we input it well. This is supposed to be, it's a small l and b dot e, caps E, let's go CL. So kindly note that this is an L, small l. So can go ahead to compute, which will solve our work for us. It takes some time depending on your computer processor. Okay, so good. That's been able to compute our work. We move to our cell voltage section, where we select our data set to be parameter estimation 2. We'll plot as well. So there is some changes in our work. Then we move to voltage losses. Also, we set our data set to steady 2 parameter estimation. And there too, you can see some changes. Go to optimization. We go down to output, power solving. We check the plots section. Then we go ahead to compute. Okay. We patiently wait for it to finish computing. Okay, so we go to our tables and we add a table which we'll name as our full load cycle. We want to import our data from here. We go to full data, look for full data. Okay, so there's our full data. So this is what we select for our work. Go on to global definitions. Add another interpolation, which we'll name as E N I is T O. So our data source will be from result table. Table will be full load cycle. We'll go ahead to name our functions, what our functions will be. E cell, exponent, full. Let's go full. It's 2. Units is S in here. Go on to our variables. We want to duplicate where we change one section to full. No, not that. Change this part. We add full. This section to as well. We change. We add full. This section. We go on to add another steady. This will be a time dependent steady, which we'll call full load cycle. Predictions. We want to change the time. 1 to 600. Want to use user controlled. It tolerance. We want to increase, reduce it. We want to modify the model. Disable first variable. We disable optimized. We also change the variables settings to user controlled, where we change the steady to parameter estimation time dependent. We don't want to generate default plots. Move to variables too. steady one, time dependent two as well. You want to also disable both variables two and optimization. You want to disable them. Steady two, so you want to do same. Disable variable two, but we leave the optimization for this section. So we can go ahead and compute duplicate our cell voltage. We call this the full cycle prediction. That'll be the full cycle prediction. Data set should be the full load cycle prediction. We want to do some manual changes to the x-axis 610. I want to change here to, we would like to plot, see how it changes. We want to change the legends to lower left. As you can see here. Go to global 1. And we want to name this as predicted. Any changes. So you're able to see our predicted ones. We go on to add global valuation. Which we'll name this as standard deviation steady one. We'll have to put in an expression for this, which will be small lb dot cops e cell xp. Go on to add, the operation should be standard deviation we want new table. It has evaluated it for us. We're going to duplicate this. Name this as 32. That will be parameter estimation, which we'll use. And we will also evaluate that data set. Go on to duplicate same, which we'll name 3. We want data set to be full cycle 3, which we'll evaluate in here. So we want to do a time selection. Want to make a range 0, 2, 1, 6, and 1. Let's evaluate. That gives us our results. We've been able to do an evaluation of this work to see within time range of this what this evaluation will be. So this brings us to the end of this work section. And thanks for following till this end. If you have any question, kindly drop your question in the comment section.